we're going to use a basketball and a mini basketball and create a momentum cannon, which is basically we're going to drop them, and then according to the conservation of momentum, this one's going to have to go up higher than it was dropped, since this one's going to stay lower. So we're going to start, we started with the masses. So the big basketball was around 620 grams, and the small basketball was 280. Then we did our free body diagram. We're going to ignore acceleration of gravity right now to simplify the equation, and then later on we'll take that into effect. So first we're going to pretend that it's an inelastic collision to find what frame of reference we want to use. So using momentum, we're going to solve to find the momentum of the system. So we take the momentum of the small and the momentum of the big basketballs. I define this as my positive direction. So as we go along, we end up getting 1.53 kilogram meters per second. Then using this number, we can find what the momentum of the whole system is if it were to combine and stick together. So 1.53 kilogram meters per second now equals the total mass, which is 0.9 kilograms times its velocity, which we find is 1.7 meters per second. So when we go over here, we're now going to say that our frame of reference is moving 1.7 meters per second in the positive direction when we do our elastic collision analysis.
Alright, when we left off, we were right about here. Because it's an elastic collision now, we can basically have both of these going out at the same velocity that came in. So this one's now going out at 6.2 meters per second, and this one is going out this way at 2.8 meters per second. We're going to call that negative because that's our negative direction. Now switching back into the frame of reference of the Earth, now this one is traveling at 7.9 meters per second up, and this one is traveling at 1.1 meters per second down. If we can find the momentum for both of these, we can check to make sure that we haven't messed up anything. So 0.28 kilograms, which is our mass of the small ball, times 7.9 meters per second is about 2.212 kilogram meters per second. 0.62 kilograms, which is the mass of the big ball, times our negative 1.1 meters per second brings us to negative 6.8 or 0.682 kilogram meters per second. Now, when we add these two together, guess what we get? 1.53 kilogram meters per second, which is exactly what we had over here.
Now that we checked our momentum and have our final velocity for both the small basketball and the big basketball, we can start calculating the final height. To do that, we're going to use energy. So we're going to find the kinetic energy of the small ball, which is 1/2 mv squared, which ends up being 19.35 joules. Then we're going to use potential energy, so finding the maximum height that goes with kinetic energy equal to 0. So we end up getting a height of 3.12 meters. Adding on to the height of the big basketball, since it's not taking off from the ground but from up here, we're estimating that in a perfect elastic collision, it will go 3.35 meters high when dropped from 1 meter.
Of course, all of these calculations are based on if the balls have a perfectly inelastic collision with the ground. But of course, in the real world, we know that's not the case. There's energy dissipated in many other forms, and the kinetic energy is not perfectly preserved, which is why, as you see, it doesn't go up the full 3 meters that we calculated, but the effect can still be clearly seen as it is more than double of the combined two. Now we can also see that from 2 meters, it goes as high as almost 4 meters, pretty much doubling in the real world the size.